Hello, just wanted to do a video explaining the MPU5's art a little bit, showing the progress so far on the MPU5. This is the fifth in the MPU line of processors that I've built in Minecraft, and this CPU uses simulated dual read registers. It has 9 general purpose registers in a simulated dual read fashion. This here, by the way, is the ALU. This here is the B side registers, and this here is the A side registers. And there are 9 A side, 9 B side registers. Each registers are mirrored on both sides. So this register here is register 1, this register here is specifically B1, and this register here is A1. And together A1 and B1 create R1, or register 1. And that's the same with all the other registers. And the reason I've done that is so that you can take any value, or you can read from any of the registers, and you can put those values into either side of the ALU. So the ALU has 2 inputs. It has the A input and the B input. And you can put any value, you can read to any side of the ALU. And when you write to the register, so register 1, you write to A1 and B1 simultaneously. So if you, so the value comes out of the ALU on this side, and it will go straight into A1 and B1. What else? Okay, so we got the memory, which is this over here. There are 32 words of memory, 32 bytes, should I say? The memory uses 6-bit address. So obviously that means that there are 32 words for the writable memory, and then there's 32 words on top of that which can be used for MMIO. This large structure on the end here is the hardware multiplier, which is an 8-bit hardware multiplier, and it's this will be memory mapped. So what else have I not mentioned? Oh yeah, this here is the hardware counter, which is just a counter similar to the program counter, that just increments every clock cycle, and you can read and write to it. It's useful for loops. It's useful for useful for division by repeated subtraction and things like that. Any kind of loop in the instruction code where you know the number of times that you're going to do the loop before you do the loop, which is quite handy. And on the back here we have 2 ROMs. So this here is the immediate ROM, which stores 8-bit immediate values for use, for instructions to be able to use, and that connects to both the A side and B side. And this ROM here is a 6-bit ROM and is used for storing pointer values. So pointers for the memory pointer, which is this register here, which is currently not connected to anything, and the program counter as well. The program counter is a 6-bit register, similar to the memory pointer. It uses you can branch using 6-bit values stored in this ROM, and you can also put values into the return pointer, which is this register here. And the return pointer is used for storing, return addresses for when they need to be used later. And yeah, so that's everything on top, and underneath we have all this messy wiring here, which will become more messy as I finish the CPU. All this wiring here is for the control logic. The pink wall is for the control lines, and the yellow wall is for the decoders. And under here we have the main instruction. So the instruction ROM on this is has 128 words, although that is split between two lots of 64. And the reason for that is because the arch that this CPU is using is quite odd, to say the least, but it's right. So this CPU will use a 7-tick clock speed. So the clock speed will be 7 ticks, and the main data loop, which is the time it takes for values to be read from a register, so for example register 1 here, to go through the ALU and back into another register, so the time it takes for that to happen is 7 ticks, and that is equal to the clock speed, which is also 7 ticks. So, and because those are equal, that means there are no read before write hazards, which is quite handy for, for the programmer, because you don't have to watch out for that. What else? This CPU uses a 3-stage waterfall pipeline, which is the same as the MPU4, where we have the first stage, which is the fetch stage. The fetch stage is the instruction ROM and program counter. Then you've got the decode stage, which is the second stage, which is all this mess of wiring down here, the yellow wiring. And then you have the execute stage, which is this, the main part of the CPU. Branching and flags on here are 2 cycles. Well, they take 2 cycles to do a branch. It takes 2 cycles to do a flag, to test for a flag. And you may think that, if it's a 3-stage system, how have I managed to get 2-stage flags and 2-stage branching? Well, there is some trickery at play here, because I am using, as part of my arch, the fetch stage. Rather than fetching 1 instruction, the fetch stage fetches 2 instructions. And that's why the instruction ROM is split into 2 lots of 64 instructions. Because for every value on the program counter, there are 2 instructions. One of those instructions is the non-flag instruction, and the other instruction is the flag instruction. And both instructions are fetched at the same time, which means that you can the instructions are which instruction comes out of the instruction ROM is chosen here using this using these pistons here, these pistons and slime blocks here, this big long multiplexer. So the bottom repeater here represents the is where the flag instruction comes through, and this top repeater is where the non-flag instruction comes through. So if there is no flag, the pistons will be retracted, and the no flag instruction will go through the top. And if there is a flag, then the instruction comes through the bottom. Okay, and we multiplex between those 2 instructions using this multiplexer. And the reason that I've done this is because this gives the flag more time to come through. So I don't, instead of having the flag be chosen right at the beginning, when the program counter is implemented, the flag only needs to be available right at the end of the instruction, which allows a 2-stage branch and 2-stage flag. Whilst having a 3-stage system, which it's quite good. Anyway, so what else? So with the flag instructions and the non-flag instructions, the flag and non-flag instructions are identical to one another. Yeah, as I said before, this is or the instruction length is incredibly long on this CPU because it uses the arch is very similar to the very long instruction word arch, which is which has obviously very long instructions, as the name would imply. And this here uses a 31-bit instruction. This instruction ROM is 34 bits, and currently we're only using 31 of those 34 bits. So yeah, the instructions are quite long, but it allows you to do lots of stuff in each clock cycle. So every single clock cycle, you're able to do loads of stuff, and the the flag and non-flag instructions are identical to each other. So you can there's no limit to what you can put on a flag instruction or a non-flag instruction. You can put the exact same instruction on flags, that you have on a non-flag instruction on a flag instruction. So you can write your entire program on the flag side if you wanted to. But yeah. Anyway, so what was I say? If you wanted to run, the idea behind this is if you want to run like conditional code, or like conditional instruction, I should say. So if you wanted to do 16-bit addition, for example, because this is an 8-bit CPU, obviously a 16-bit addition requires that has to be done in 2 steps. So the first step, you add the 2 lower bytes together. So you would do that to begin with, and when you do that, you would test carryout, which is this here, and the carryout will, carryout is bust from the top here, bust all the way down, and it comes through and down to the pistons down here. So these pistons will then either choose between the flag or the non-flag instruction. So when you go to, first of all, you add the lower bytes together, and then you add the upper bytes together. When you add the upper bytes together, you would have, in the non-flag instruction, you would just have a normal, you would just add the upper bytes together normally. However, if the flag activates, so you're on the flags, the flag instruction goes off. If the flag instruction goes off, that means you need to add the upper bytes together with a carry. So adding them together with a carry, because there was a carry out from the lower bytes, and you're able to do that. If you were just doing a 16-bit addition, you would have to insert a null in between the 2 additions because of the flag. The flag takes 2 clock cycles to come through. But yeah, so what else do I want to say? The main benefit of this, doing things this way, is that you can run conditional code without having to do branches, because conditional branches are incredibly slow. If you wanted to do a conditional branch, you would not only have to test the flag, but then after testing the flag, depending on whether or not the flag is positive or negative, then you would then have to do a branch, which would then take a further 2 clock cycles. So to do a conditional branch, you'd have to do 4 clock cycles. And sometimes you do need to do conditional branches, and you can do conditional branches, although they do take 4 clock cycles. But if you can get away with not doing a conditional branch, and you can just get away with doing the conditional code you need to do in place, then without branching, then that's a lot faster. You're saving 2 clock cycles. What else? What was I saying? There are many programs that I want to run on this computer. I want to be able to run program. Well, I want to be able to do stuff that the MP4 wasn't able to do, because the MP4 in many ways fell short. On the MP4 I was meant to be doing 16-bit pi and stuff like. Oh yeah, by the way, whilst I'm thinking of it, this thing on the top here is the BCD display. It just takes a 16-bit value and displays it in binary. So that's the main output for this computer, or for the CPU. So yeah, that's what that big thing is at the top there. It's causing a huge shadow. Anyway, the goal for the MP5 is to mostly do what the MP4 couldn't do. So there were loads of things that the MP4 failed to do. It failed to do 16-bit pi. I was only able to do 8-bit pi, and I would like to be able to do other things like Mandelbrot on this, and do Persian, such as recursive fib and recursive factorial and whatnot. And I'd like to be able to do other interesting algorithms like list sorting and like square root. And as well, I'd like to be able to hook up some I/O, so some way of having the user input values into the computer once it's running. And if I'm able to, if I can, I'd like to have like 8 levers so that the user can input a byte, and then from that, I would be able to create something like a higher or lower game, which the user would be able to play and be able to guess the number. CPU would calculate whether or not it's higher or lower, and it's rather basic, but still interesting nevertheless. I'd like to also be able to do Brazenham's line drawing algorithm. I will hook up a pixel display to this. I do have a 16:8 pixel display to hook up to this. It'll be the same display that the MP4 used. But yeah, so it's only a very small display, but because the CPU is, it's only got 7-tick clock speed, it doesn't run that fast. It doesn't really run fast enough to warrant having a larger display, or because each pixel needs to be drawn manually, one clock cycle at a time. So it's not exactly going to be fast at drawing things on the display, but the idea is there. So this is the MP5 so far, and thank you for listening.